Thank you. So now let's move on to the next presentation. Benedikt, he will talk about what's the challenge with the ISO standards.
Yeah, thank you so much for having me here. Today, I would like to talk about the very exciting topic of standardization. So I can really grasp the excitement in the audience here. My name is Benedikt Koelsch. I am a postdoctoral researcher at Cerema in France, together with Valérie Leprince, who has already talked today. And I will talk about the ISO standard and the challenging things and possibilities of improvement in this standard. Yeah, we have talked a lot about airtightness and why this is important. Of course, we have the energy issue there. We have issues of thermal comfort and moist formation inside walls. And as Valérie already told us today, in large detail, there's an increasing number of tests performed in Europe, and these testings is an important part in a lot of national regulations in European countries. This testing is mainly used for measuring the air leakage to in these buildings to fulfill these energy performance standards, to compare different buildings among each other, or to determine the reduction of air permeability after renovation is done. This measurement is done mostly by the ISO 9972 standard, which is shown here. This standard has been referred to in the previous presentations a lot, and it describes the measurement procedure and calculation methods to determine the air tightness in buildings. To be able to compare and to make these results credible, which is important for the energy regulations in Europe, the results need to be reliable and valid. They need to be, and this for different kinds of buildings. So for small buildings, for large buildings, different shapes of buildings, they need to be reproducible even under very challenging environmental conditions. So if we have wind or large temperature differences, and they need to be consistent with other standards like the ASTM E779, for example. Recent works, especially in the AIVC community here at the AIVC conferences and journal publications, and the experience we have in Europe with these lot of tests, there was a need among the community to really revise and improve the current methodology described in ISO 9972. So therefore, Cerema set up a working group of international experts to collect data and knowledge from these experts in the field, and to provide this for a possible revision of the ISO standard. So we would like to know better the improvements of the standard to allow the performance of the test even under challenging conditions, to make it more reliable, improve uncertainty calculations, and make it more consistent with other standards. So therefore, we conducted a survey among these experts, and to collect a comprehensive list of issues that needs to be improved probably in the standards. And this working group is then divided into sub-working groups working on these subtopics relating to the interests and expertise of the experts in these respective fields. However, I would like to highlight this should not be a formal revision of the standard. This should gather the best knowledge of experts in the field as a basis for an official revision in an ISO technical committee later. That just to show you some affiliation or the affiliations of the working group members. So we have researchers from research institutions, universities, mainly from Europe. We have Buildwise, we have Cerema, of course, We have Berkeley Lab as included. We have on the other side distributors and manufacturers of blow-odor measurement systems like Retrotech or Energy Conservatory, Wöhler, included in this working group to really get the knowledge from the experts in the field and the theoretical knowledge of the researchers together here. Yeah, what are the reasons behind the necessary revisions? First of all, there are some limitations in the standards regarding the measurement reliability. Reliability means that the result of the measurement is consistent and reproducible over time. So I will go through all these points very quickly. So the first point is building preparation. The standard says how intentional openings should be sealed and closed or left open during the test. However, if this is not precisely described, this can introduce some differences in the final results, and can depends on the conducting technician, reduce the reliability of the results. So we would like to avoid these ambiguities in the standard. I always show for all these points here the current status we are on. So we have not started on this particular point. Then the standards requires to take wind measurements, wind speed measurements, and temperature measurements. However, it's a bit unclear in the standard on where or how or if to measure the wind speed and ambient temperature in the standard. So we gave recommendations for temperature and wind measurements. So this is already done in the group, in the sub-working group there. Then it's important to really define the placement of external pressure taps. So if we're conducting the pressure difference between inside and outside while simultaneously measuring the airflow, we put pressure taps inside the building and outside the building. And this location is used as a reference for each pressure station and for zero flow pressure measurements before and after the actual measurements. However, this is not really clearly stated in the standard. It says in the ISO standard, it should be at some away from other obstacles or the building, but it's not really clearly stated. For example, in the ASTM standard, it's really recommended to put the pressure probe next to the building and recommended to average it on all facades. This, especially for zero flow pressure measurements, these taps the location of these taps should be more clarified. So if it should be placed next to the building or farther away from the building. So we are on it, but this is probably a bit more research needed. Next, there's the duration of the pressure meant and airflow. In this, the standard says that should be, at least for the zero flow pressure measurements, the measurement should be averaged over 30 seconds or more. But this is really influenced the reliability of the results, especially in the presence of wind. So we recommend to do it at least 60 seconds or to adapt it according to the variability of the wind speed, for example, or the zero flow pressure measurement. As Ian pointed out, there's in the multi-point test in the ISO standard, we need different levels of pressure to be tested that we are able to perform a regression. And the number and level of this pressure difference may influence the reproducibility of the test. And in comparison to the Canadian standard, for example, in the ISO standard, there's no single point tested or like no option of single point tested included. So this might be a good idea to include a single point testing in the ISO standard as well. Yeah, speaking of regression, we have, if we are measuring as required in the standard multiple pressure points, we are performing a regression for all these pressure points to, for example, for the French regulation, obtain the airflow rate at very low pressure differences at 4 Pascal, or in Netherlands at 10 Pascal. The ISO standard recommends to use a least square regression to determine the airflow coefficient and pressure exponent in this regression. However, this regression doesn't take into account the measurement uncertainty, and it only optimizes the distance between the measured point and the regression line in y direction. This is valid, this assumption, if there are no uncertainties or negligible uncertainties in the pressure, and the uncertainties in the airflow are the same for all, or in the same order of magnitude for all pressure, for all measurements, which is not the case in real life. So authors recommend to use a weighted line of organic correlation, which uses the standard uncertainty at each pressure and airflow point as a weight for a possible regression of all the data. And additionally optimizes the distance in X and Y direction. So you can see it here on the graph. So the blue line, these are the measured pressure points here. And you see the standard uncertainty showing at the arrow bars here. And the ordinary least square regression try to find the best fits for all of these points equally, whereas the weighted line of organic correlation weights the points with a less standard uncertainty of the measurement higher. So you see for these points here at higher pressure differences, the fits is better. Even though at that point, it's probably makes not a big difference at 50 Pascal, it makes a big difference if we extrapolate to lower pressures at that point. Additionally, literature has shown that this improves the predictability of the airflows and reduces the variability and flow coefficient and pressure exponent. Yeah, and then there are limitations on the validity of the test. So validity means, do I really measure the value I intend to measure at the end? There are some things in the standard as well, like airflow corrections. The ISO requires to, as all the other standards, requires to correct the measured airflow to standard conditions of temperatures and pressures, so that different tests can be compared in different locations. However, the ISO standards allows a simplification of this correction, which assumes that the barometric pressure is negligible, the blower door is calibrated close to reference conditions, and the pressure exponent is close to 0.5. However, for example, the ASTM standard doesn't allow this simplification. I think, given the modern computing equipment and that the it's already implemented in the software due to the ASTM standard, I think, Colin, you agree that this is the non-simplified version is already implemented in the software because to be able to test according to ASTM standards. We think the simplification is not necessary anymore in the ISO standard here. Then there is some uncertainty due to the calculation of building volume and area. As Valerie and Ian already pointed out, each country has different measures to calculate the building volume and area. So some countries calculating the building volume excluding the internal walls, or some excluding the internal walls, calculating the inner volume or the outer volume, or calculating the surface area, including the floor area, or like France, excluding the floor area. So they are really different measures to getting the derived quantities of the airflows. And it's really hard to compare these values among all these different countries. So it would be convenient to have a standardized method. However, this is really, there's a huge discussion on this. So if we should leave this to the national regulations or if we should put it in an ISO standard. So this, we need to see what's going on there. Yeah, and then speaking of zero flow pressure measurements. Zero flow pressure measurements are the measurement done without pressurizing the building before and after the actual measurement. So it functions as a kind of baseline pressure before and after the building is pressurized. And as Ian extensively gave a presentation about, or like the previous speakers as well, about high-rise buildings, there are very large zero flow pressure measurements due to stack effect there. However, ISO 9972 has a strict limit that the test is not valid if this zero flow pressure measurement is larger than 5 Pascal. And we saw in the previous presentation that this can be like easily exceeded for large building, this limit. So even though, and this constraint is due to, it should limit the influence of wind and temperature on the uncertainty, but there are other things influencing this as well, like the leak distribution in the building. But the problem is that this constraint in the standard really excludes high-rise building from being tested according to the standard. Of course, I can test high-rise building, but if I have to test, like in France, all the buildings, according to the standard, and these are excluded from the standard, it's a problem at that point. So this is really a thing which needs to be rethought again. So one possible solution would be, for example, to only recommend this as a zero flow pressure. So to say, okay, we recommend to stay below 5 Pascal, and additionally include the zero flow pressure in an uncertainty calculation, and maybe the variability of the zero flow pressure as well. So this is something which we started to work on, but there's still some work needed on this. And I mean, if you have any recommendations or discussions, I'm very open to discuss this topic with any of you or experiences. And finally, the knowledge of uncertainty. There are two kinds of uncertainty in the standard. The first one is due to the measurement instruments, measurement protocol, and analysis. So, for example, the errors due to the measurement devices itself, which are given in the standard. And we revised this part to that every measurement device has to give the error according to the maximum permissional measurement error to be used as an influence parameter in the uncertainty calculation. So this has finished. And then there are some inclusions possible to include uncertainties for building preparations, reference values, or sampling of buildings. We have talked about sampling as well. But this is more difficult. I think the German annex, for example, includes some standard values for this in the uncertainty calculations, but this has not been started yet. And then there is the errors arising from physical model assumptions. The standards assume that we can approximate all the single leaks as one big leak, which fits to the power law. So, but in reality, every leak has its own pressure exponent, and so if we would make it really good, we should measure every leak and then measure the airflow through every leak. But that's not possible because we don't know the leaks. But due to the non-linearity of this equation, it introduces like a model error to sum all these up. And this increases with high wind speed and stack effect. But there's more work necessary to really understand and quantify these errors. Yeah, finally, I would like to show you some preliminary results we did from a simulation we recently did. So we tried to quantify the flow error arising from different parameters. So we did a simulation of 3 million different buildings with different pressure exponents, different leak distributions, different pressure coefficient distributions, and different wind speeds on the building from 0 to 10 meters per second. And these are some preliminary results. So you see here on the y-axis, you see the calculated flow error, and on the x-axis, you see the pressure station we are measuring. So like 50 Pascal, 60 Pascal, 70 Pascal, 80 Pascal, or so on, divided by the calculated zero flow pressure measurement. So this means if you have a very small, this should show you the error of each pressure station according to the measured zero flow pressure measurement for like all large different variability of pressure of buildings. And the aim was to see, can we define some maximum uncertainty for this? So this, if you have a very small delta P0, this graph here, the both ends are getting very high. And if we zoom out, this tends to 0, which makes sense. So, but if we have a very large delta P0, so we're getting closer to 1, the error increases. And what we did then, and this is shown here, we thought, okay, this is like a bit messy, this graph. Can we show just the just the configurations which occur very likely in reality? And there, a lot of these simulations are where most of the leaks are on the windward side, and none, or like a very small portion, are on the leeward side. And if you see a building, if you have a square building and there's wind blowing on one direction, you have one facade is covered like the windward side, on 3 facades plus roof are the leeward side. So it's very unlikely that all these leaks are only on the windward side. So we excluded these points and said, okay, we make it more reasonable. And then all the gray points disappear and we only have the black points. And this is very interesting. With these black points for the more reasonable, this is the results for a pressurization test. We can define like a curve of maximal possible error here, like this point. This is the fit of this maximum curve points here. It's given here and over there. And it would give you the possibility, if you have a measured zero flow pressure and you have a pressure station at like 50 Pascal, you can give for this pressure station the respective error. Additionally, in the standard, it is said that the first pressure difference measurement should be 5 times higher than the delta P0, which would be this point here, like so. And this indeed would make sense. So we would really exclude very large errors from the beginning and would start like with, so this limitation in the standard would make sense. But this, I'm happy to discuss this later with you. And this is just some work we had done to really try to quantify the flow error due to wind on this topic. So the next things are, we would like to do until mid-2023, give a proposal for to revise all the things which are ready to revise, until end 2023 to give a proposition for new things, for all the things which need research, and from 2024 to really propose this a new ISO on ISO level. And here I'm thanking you very much for your attention. My name is Benedikt Koelsch, and I'm very happy to answer all your questions now or later in the discussion.
Thank you very much. We have time for 1 or 2 questions. So if any questions, feel free to put hands up. Any question? And also to the online audience, if you have any questions, so please use the chat box to write your questions, and then we are happy to answer as well.
Yes, thank you. Thank you for this overview. Just for clarification, in the final error calculations, the simulations that you showed, the zero flow pressure, it includes as well the effect of wind and stack effect?
Indeed, not stack effect, but wind. This stack effect is not included yet in the calculation.
That's not the point. The ratio between the
Microphone, please. Online audience couldn't hear.
Yeah, this is the ratio between the measurement point and the zero flow pressure. So whatever the zero flow pressure is due for, it can be due to wind, it can be due to stack effects. The most important thing is that there is a zero flow pressure that is above 5 Pascal, or that is big. So this is the error, the mathematical error due to the ratio between pressure station and zero flow pressure, and no matter where the zero flow pressure comes from.
And it would allow to include the error due to the zero flow pressure and an uncertainty calculation instead of just setting a limit of an arbitrary limit of 5 Pascal or something. So.
Yeah, but because you gave the example of some configurations that are quite unlikely with the example of the windward facades where all the leakage is. So there's simulation behind assuming wind pressures and
wind pressures, of course, not no stack pressures, but wind. Yeah, wind pressures are like the thing. Yeah, indeed.
Thank you. So look at the schedule. So we will bring our last speakers for the morning section. And if you have any questions in terms of this presentation, we have time in the discussion section.
Good. Thank you so much.
So the last